Hi everyone, welcome to seminar. We're once again happy to host an international scholar who has come to give us a presentation. We have Dr. Mario Conde Frias. So Dr. Mario Conde Frias is an assistant professor in the Physics and Geosciences department at Universidad del Norte in Colombia. His research primarily focuses on hydrodynamics and sediment transport in freshwater and marine ecosystems, characterized by large and complex bottom movements, such as seagrass, metals, kelp forests, and coral reefs. Dr. Conde Frias has also investigated the dynamics of coastal and estuarine systems through field observations and numerical modeling of nearshore processes, involving gravity and infragravity waves, and their implication for coastal erosion and flooding. So please welcome.
Thanks everyone for having me here. I'm very glad that you could attend this talk. As Adriano was saying, today I'm going to be presenting main findings of my result from my PhD. I did my PhD in the University of Western Australia, and now I have a position at Universidad Norte in Barranquilla, Colombia. So the talk today is going to be about the near-bed hydrodynamics in aquatic vegetation and the implication that understanding these processes have for sediment transport. So as you may know, aquatic vegetation is ubiquitous in river and coastal systems. We know that these ecosystems are quite important because they provide a wide range of ecosystem services like biodiversity promotion or riverbank stabilization. However, because we know, even though we know the importances of this ecosystem, the near-bed hydrodynamic, which govern a lot of critical processes such as sediment transport, hyporheic exchange, or even biofield formation, needs to get more of insight of this hydrodynamic in order to be properly addressed. So still we know that we have some physical, some knowledge gap in understanding the physical processes that cover those interactions, and this is kind of the idea of this talk. Basically, I'm going to focus on the sediment transport and the idea of characterizing that near-bed hydrodynamics in vegetated flow. In this case, I'm gonna try to show you the result for emergent case, which can be a subrogate of mangrove forest, and also for submerged case scenario that is kind of like a subrogate for seagrasses, understanding that the study that we are doing here is a physical model of seagrasses where we are not considering flexibility, for instance, but just want to get properties of the hydrodynamic properties of the flow, like stresses and drag. So just to quick overview of what we are talking. So when we have a flat plate and there's no vegetation at all, this is kind of like the traditional development of a laminar flow over the flat plate, where as you can move through the plate, you start getting eddies, and eventually the flow becomes fully turbulent flow. And basically we can define the extent where there is interaction between the flow and the effect of the bed into the flow, and we call that the bottom boundary layer. And technically, we define the bottom boundary layer as a percentage of a free stream velocity, which is the velocity above the bed at certain height, where there is no influence of that one. So when we have bird bed scenarios, we have a quite well understanding of what are the velocity profile, or how the velocity profile looks like. We can even divide this velocity profile in different kind of layers that we know pretty much the physics of the total stress within those layers. And basically this total stress, when you have this flat plate, it kind of like divided in two types of stresses. One is what we call the viscous stress, and the other one is what we call the Reynolds stress. And then if we add them together, then as we say, you get the total stress. So visual stress is an important parameter for predicting sediment transport. And basically, there is a lot of techniques that people have developed for bare bed in order to predict this visual stress. However, when we move to vegetation, you will see that the things change quite a lot, because all the stems or all the roots or the leaf of the vegetation will create turbulence, but you're also going to have an additional drag into your flow to the field and the flow field, and this will alter the shape of the velocity profile. So therefore, if you see here, this is basically a top view of a canopy. So this is the same array that you have here. Imagine that you just take a slice and you look at it from the top, and this is the velocity field that you will get. So you see that now the velocity field is quite heterogeneous across the domain, which actually, if you look at it in the vertical, so basically now I take a slide what the dashed line is and see the vertical profile across the elements, you will see that you will get areas with high velocity, areas with even a small velocity, or even with velocity reversal at the wake of the elements. So in that case, when you have this high heterogeneity in the velocity field, you might also have a new term that will add to the total stress term that I just mentioned, that is called the dispersive stress. So now, if you really want to understand the dynamics or the hydrodynamics in vegetative models, you need to somehow measure velocity fields quite accurate. And if you want then to study the near bed region, then you need to do that very close to the bed. So in order to do that, we need to define that bottom boundary layer region. So we need to somehow say, okay, what's going to be this 99% of the velocity that we used to define in the variable scenario? So for that reason, today in the presentation, basically I'm going to be talking about two topics. The first is trying to understand how aquatic vegetation can alter the near bed flow characteristic, and we're going to do that we did that by combining laboratory measurements and numerical simulation. But also, we wanted to solve this specific question, is that can we actually develop a model for predicting that bed shear stress in the presence of vegetation? So as I was saying, there is a good amount of knowledge of how to predict bed shear stress in bare bed scenarios where there is no vegetation, but how can we now move forward to get a model for bed shear stress, and then analyze if with this new model of bed shear stress, we can actually say something about bed load transport that are basically models that relies on a proper estimation of the bed shear stress. So as I said, I'm going to use numerical simulation. Basically, we're going to use LES modeling or OpenFOAM, and we're going to use high resolution particle image velocimetry to try to get those velocity field that we need for the near bed hydrodynamics. So this is kind of like a summary of the cases that we assess experimentally. So we have three elements in a staggered array to simulate the vegetation. So kind of like something in the middle between a fully random array and something that is a square or organized array. We change density from 0 to 1.7. This is what we call the frontal area per unit of the area. We'll define it later, but just keep in mind that we tested different densities of the vegetation. We tested different velocity in order to kind of increase something that we call the Reynolds number, which is having different type of flows, but most of them were turbulent in the scenario that we were evaluating. And we also changed the depth ratio, which is the ratio between the water depth and the height of the canopy. As I say, I also did emergent, so there is a missing one there. So there is depth ratio of 1, 2, and 3.6 because we test emergent cases. And then the numerical cases, we also use the same configuration. We put cylinders in a staggered array. We also change density even for denser regimes. We kept the velocity constant, so we just test one Reynolds number for the numerical case, and we test two depth ratios, depth ratio of 1 and depth ratio of 2. So this is kind of like the universe of data that we had available for studying the near bed hydrodynamics. So as I was saying, if we want to understand what is near bed hydrodynamics, somehow we need to come up with a definition of a bottom boundary layer for vegetative flow. So the first case that I'm going to present is what happened with emergent vegetation. So basically, when you have emergent vegetation, as I was saying, you can know that you will expect additional drag exerted by the vegetation, and you're going to have additional turbulence produced by the wake of the elements. So this will make that the velocity profile looks at this form. And what we did was that we tried to characterize how this profile looks for different densities of the canopy that were calculating using this parameter that we call lambda f, but the name is frontal area per unit of bed area. So basically it's just the ratio between the frontal area that you see if you have the rod, so it will be the diameter times their height divided by the area where the rods are. You can extrapolate that with what people does in the field, that is just try to count how many dots you have dowels you have per square meter, and that will be the same idea of the density of the canopy. So the higher the number, it will be more elements in a small area. So what we did is that we decided with experimental measure trying to take measurement at these 4 transits or these 4 locations originally. So one behind the dowel, one in the two in the center channel, and one in the front of the dowel, which is this number 2. And when we looked at those velocity profile, they look like this. So each color represents each of the location. So basically, as you can see in the full velocity profile, you will see that the velocity has an overshoot region. So it means that the velocity actually goes to a higher value, then it goes back, and then gets a stable value or a constant value across the water depth. So the best idea, it was also strategic, is to define the bottom boundary layer, or the height of the bottom boundary layer at the first point, at the first vertical point where you get the constant velocity value. So basically, it's this height that you were seeing here. So we were trying to get a monotonically increase of the velocity. Once we reach this average value, this is what we defined as the height of the bottom boundary layer. So basically, what we wanted to know is, okay, how this thickness of that layer changes with the properties of the canopy. So if we change the flow regime or if we change the density, if that region becomes thinner, thicker. So that is the start of the research. So once we know, or we got this definition of the bottom boundary layer thickness, we could start looking at their behavior, its behavior with different canopy properties. So the first one that we did is that for all the measurement that we have, experimental and numerical, we wanted to see the behavior of the bottom boundary layer thickness against the canopy density. So what we found was that there was a monotonic decrease with the density, which means that the bottom boundary layer thickness was getting thinner as the canopy was getting dense. This is for, keep in mind that this is for emergent vegetation. We also tested for different Reynolds number, and we found that there was an impact of the Reynolds number, but it's a small impact when you compare it with the density. So we, from this part, we pretty much knew that the bottom boundary layer thickness was mainly controlled by the density of the canopy that we have. So when we quantify how much is that, because if you see, this is a kind of like a dimensionless bottom boundary layer thickness, we were able to notice that in absolute value for the range of density that we use, the bottom boundary layer thickness was between 1 millimeter to 6 millimeters, which is quite thin region. Why this was so important? Because the way that we define that region actually make us to understand later on the scale or the length scale where we can capture that stresses. And basically, if you measure anything outside that region, you won't be able to properly capture visual stresses or any term of the total stresses that I was mentioning before. So it poses the challenge that this is kind of the result of the PAV measurement, and this is kind of in a real scale, the area that I need to properly measure and quantify to get high velocity fields. And also keep in mind that I'm doing this in different locations and then to get a spatially average. And the reason for doing that spatially average is to kind of get rid of all these fluctuations that you get in different locations. As you see in the previous slide, there was these different values of the velocity profile at different locations. So we ended up using the spatially average between these 4 points as the spatially average of the parameter, which is the bottom boundary layer thickness. So then, as I was saying, we decided to look at the structure of the stresses within those regions. So once we had this velocity field, we were able actually to determine for different densities how the viscous stress behave within emergent case, how the Reynolds stress behave, which is these red points here, and how the dispersive stress behave. So what we found is that within this region, as you get closer to the bed, of course, the most important there is going to be the viscous stress. Remember that we are in a flat place, so there is no roughness element added to it. So you expect to have a viscous sublayer forming as well. And basically, if you are able to define properly the viscous stress, you will know that if you don't dimensionalize that by the visual stress, then you will get an estimate of the visual stress. But then, as you go away from the bottom, then all the stresses, the rest of the stresses term become important. So for emergent cases, what you're gonna find is that there is a region from quarter of the bottom boundary layer thickness to the 3/4 where the 3 stress terms are important equally. So basically, if you measure here and you say, for example, if you are able to measure at 0.5 the thickness of the bottom boundary layer, which if you keep in mind the number that I say, it means that you can even measure at 3 millimeters or at 0.5, based on the thickness that we have. And you decide to test or say that the visual stress is equal to the maximum Reynolds stress that you will find, you're gonna underestimate the visual stress by 50%. Because even there, which is where you get the peak of the Reynolds stress, is underestimated the real value of the visual stress. And that was something that at the beginning of the PhD was the big discussion, because everything started with some question that was, for sediment transport, what is the main driver? Is it gonna be the visual stress, or is it gonna be something that people came with the idea that is called the turbulent kinetic energy? So people were trying to do measurement of visual stress, and they were finding that there was not a good correlation with the sediment transport processes. So the whole conclusion was visual stress is not suitable for getting bed load transfer measurement. So once they started doing the turbulent kinetic energy correlation and the bed load, they were finding good correlation. But there was some missing link, because we were saying, okay, why the visual stress is not working? If physically speaking, the stress is what actually causes the motion of the sediment. So they were saying that was the whole idea of the communities, is because the turbulence is more important than the stress, or the turbulence that is produced by the visual stress is not important. But what this result was showing at that time is that probably they are underestimating the visual stress. Probably they are not being able to properly capture, given the fact that the bottom boundary layer is quite thin, and with the instruments, getting velocities at that resolution was very challenging for many of the previous studies. So because of that, we decided to create a model for predicting visual stress. So we know that it's quite challenging to get measurements to actually get a proper value of visual stress. So let's try to get a model from properties that we can extract more straightforward, like flow, velocity flow, or even canopy properties like the density. So what we decided was to take again the total stress, which is, as I was saying before, is the composition between the viscous stress, the Reynolds stress, and the dispersive stress. And we know that because of the non-slip condition that you have in a smooth bed, and also as the bed is impermeable, you know that at the bed, the dispersive stress and the Reynolds stress has to decrease, and therefore the only important term will be the viscous stress. So basically you can approximate the visual stress as the viscous stress at the bed, or kind of like the gradient of the velocity when you go as close as you can to the bed. So with our velocity measurement, we can actually estimate that. So you remember that I was saying that when we define the bottom boundary layer thickness, we were assuming that it's gonna be the height at the first time that the velocity reaches the unit for value. The reason for that is because we can assume that for all the canopy densities, the profile will be self-similar in that region, which means always monotonically increasing before actually seeing the overshooting processes that we were looking at in reality. So based on that, you can approximate the visual stress as the ratio between a reference velocity and a thickness length. In this case, it's going to be the bottom boundary layer thickness. So we are saying it's self-similar within the bottom boundary layer. So instead of having the gradient, we're going to say it's going to be a reference velocity and the thickness of that layer. So if we were able to get the thickness of the bottom boundary layer and define that reference velocity, we're probably going to have a model for estimating that visual stress. So this is what we did. So we need to get into the task of trying to understand what was this reference velocity. As if you know, if we are assuming self-similarity, the reference velocity has to be the velocity at the top of the bottom boundary layer, because that's going to be the reference that you have for the velocity, and then the thickness of the bottom boundary layer. But then when we compare that velocity with the pore velocity is the velocity taking into account that the flow is not moving freely. It will have some elements that will be obstructing. So you'll have kind of like an increase in the region where there is no downwards kind of like of the velocity. So this is what we call the pore velocity. It's just the pore velocity divided by porosity. It's kind of the idea. So we found that the pore velocity was within 10% of the velocity at the top of the canopy. So this was the velocity that we use as a reference. This velocity is straightforward because it's just dependent on the flow. If you have a discharge, then you can take the discharge divided by the area and then divide this value by the porosity and you will get this. And then we tested with the measurement that we have of visual stress, and this is what we found. So again, here you will have the measured vector stress in the x-axis, and this is the model that I was saying. This is just the velocity at the top of the bottom boundary layer thickness divided by the bottom boundary layer thickness for all of these canopy densities. Again, this is emerging cases, and you can see here that this also was done for two different Reynolds numbers, that the model was performing well except for these type of points that you were having here. So when we look closer into this, you can tell that all these set of points that are not actually matching properly were cases where you have very high Reynolds number. You can see that the dark green and the dark purple in the points, but also were points that has very small density, which means that what probably is happening is that if you have a flow where you have a canopy that is not dense enough and you have high Reynolds number, it's most likely that what is controlling the nearby hydrodynamic is not anymore the canopy, it's again the bed. It's kind of like you have sparse cases where there is no much effect of the rods into altering the flow field, but you are getting all of the event based from the normal transition that you will get in a bare bed case. So we decided to test that hypothesis, saying, okay, well, if that is the case, it means that our model relies on defining properly the length scale of the bottom boundary layer thickness. But if you have a case where the bottom boundary layer thickness is not controlled by the canopy, but it's again controlled as a bare bed case, then we need to define or kind of like improve our model, defining what we call the effective bottom boundary layer thickness. The effective bottom boundary layer thickness is basically the minimum value between the bottom boundary layer that we just defined or the bottom boundary layer that you will get if you have a bare bed. This comes from the fact that you can approximate the vector stress in a bare bed as a friction factor, as a drag from the bed, and a reference velocity. So if you do that, you can actually get that height of the bottom boundary layer if you have bare bed. And basically what we are saying is, if the canopy effect is more important, then you're gonna have a very thin bottom boundary layer. If the canopy effect is not important, then the thickness will be actually controlled by the bare bed scenario. So when we incorporate this new effective bottom boundary layer, then we get a better way better prediction of the vector stress. So there we have it. We say, okay, well now we have a model that as long as we can get the bottom boundary layer thickness and we can get this reference velocity, we can get estimation of bed shear stress. So we then decided to move for the submerged case. So it turns out that the submerged vegetation actually is a more challenging question, because here you will have flow that will have the water there will be higher than the vegetation, that's why it's submerged. But then you will have a part of the flow that the velocity will be reduced by the drag exerted by the vegetation, and then you will have other part of the flow that is not affected by vegetation that is going to be faster. So basically, these differences in the velocity creates another turbulence scale that we call the canopy-scale turbulence. The main effect, the name that we use is Kelvin-Helmholtz instability. So this is kind of like a roller vortex that forms at the top of the canopy. And depending on the density of the canopy, these vortices can be confined just to a layer around the top of the canopy, which is what you can see here. Or if the canopy starts becoming sparser, then you can get these vortices actually penetrating all the way to the bed and altering the nearby hydrodynamics. So what we wanted to know is, okay, can we use our predicted model of vector stress for submerged vegetation? Would it work just for dense cases? Would it work for sparse cases? What will happen when you have transition and that you have these vortices actually altering the whole hydrodynamics and therefore altering the structure of the bottom boundary layer thickness? So this is just a representation of the velocity fluctuation. This is taken from the PIV. So this is an animation that I create based on the PIV measurement. And what you see is that you sometimes will get these big vortices actually creating sweeps that are high momentum fluxes that goes from this layer into the canopy, and then you will get also ejection events. So you can see that the whole velocity field within and above the canopy is actually being altered by them. So as I was saying, we did the same test, right? So this is the model that we have for emergent vegetation, where I just showed you before. This is kind of like this was the line where all the relation between the bottom of the layer thickness and the density for emergent case. And when we did that for the submerged case, this is what we found. So basically, as I was saying, we were able to change the Reynolds number. We were able to change the depth ratio. So all the red colors are the high submerged canopy, which is 3.6 times. So the water depth will be 3.6 times the height of the canopy. And the other cases that we test was when the water depth was twice the canopy height. So these are the blue color. So what you can see straight away is that the bottom boundary layer thickness of the submerged case scenario is actually thicker than the one that you expected in the emergent case. This kind of the thing. You will see that there is important variability with the submergency, but what you can see is that the most scatter happen in the transitional regime. So it's in the regime where you have these big vortices that actually can penetrate all the way to the bed. So as we could measure the thickness of the bottom boundary layer, we could actually be able to test our model for the shear stress. And before doing that, we decided, okay, let's just measure how is the behavior of the shear stress with the density. So these three regions here are the same three regimes that I just defined. This is the dense regime, this is the transitional regime, and this is the sparse regime based on the density of the canopy. So what you find is that in general, the shear stress decreases as the density increases. This is something that people expect, because you expect that as you have denser cases, then the velocity within the canopy is smaller, and then the shear stress that you will get should be smaller. So you can see that. But then as you start becoming sparser, then the shear stress resemble more to the bare bed condition. If you see here, this is the density 0, it's just not aligned here, but this is the case with no vegetation. So you see that as the canopy becomes sparser, it's actually going towards the bare bed scenario. So we also tested for the different Reynolds number, and then you get the same. It's like the higher the Reynolds number, the whole Reynolds number, you're getting changes in the shear stress. So in general, we decide to look at the structure based on the previous result of the total stress within the nearby region in submerged vegetated flows. And we find quite interesting result, and is that when we were looking at sparse vegetation, and you see how, the behavior of each of the stress terms, you could see that the sparse case scenario resemble to the bare bed case. So basically, submerged vegetation have a stress structure that is quite similar to the bare bed. Of course, you will have some changes in the dispersive stress, because still the vegetation is altering the velocity field, and therefore you're still going to have heterogeneity in the velocity field that will induce a form stress, which is this dispersive stress, compared to the bare bed that you can see that is always 0. But in general, you get the same behavior for the bare bed. But then when you compare to the dense submerged cases with the emergent, you also see that they are very similar, which means that apparently we have two limiting conditions where dense submerged vegetation, the stress structure resemble to the emergent case that we just studied, and the sparse submerged case resemble more to the bare bed. So with that in mind, we decided to just jump straight and test our model, and this is what we found. So basically, if we use our model of shear stress, as I was saying, we need to define the reference velocity, that in our case was the porous velocity, the pore velocity, and then the effective bottom boundary layer thickness that I just said. So we were able to compare for different densities the ratio between the measured shear stress, which is this, and the model that we are proposing, which is this one. So this is -1, so it's just we are just dividing the two terms, and you see that you get good representation for the dense case and for the sparse case that, it's still transitional, but it's actually close to the sparse regime. So basically the model is kind of reproducing the shear stress for submerged, for dense case and for a sparse case. But we got a big scatter in this area, which is the transitional case. So the transitional case, if you recall, is the one that I was telling you that you have the vortices altering the whole flow hydrodynamics. So what we decide to do is, okay, our effective bottom boundary layer thickness relies on the fact that we need to define properly a reference velocity. And if you recall the velocity profile that we have in sparse, in submerged vegetation, as you go transitional, it's very hard to get a reference velocity out of this profile. Like there is nothing that will tell you exactly what will be the reference velocity. When you get dense, you still start getting some shape similar to what you get in emergent, so you can roughly say, okay, yeah, this will be close to the emergent case. So we decide to use the depth average velocity within the canopy layer. So basically we average over the entire canopy region and use that as a reference velocity for the transitional regime. And then redefining that reference velocity allow us to check again the bottom boundary layer thickness for submerged case. And what we found was that this is the definition of the reference velocity as we change density and Reynolds number. So we define that. And then when we test with the new reference velocity, our vector stress model, we got a way better result compared to the previous model. So we could actually say that as long as we define properly the reference velocity within submerged vegetation, you will be able to also get prediction of best shear stress. Keeping in mind that the reference velocity will be for the transitional regime, the depth average velocity of the canopy, which is this one that I was just telling there. So then we wanted to test our model or what are the implications of having now a correct model of best shear stress in terms of sediment transport, right? So this was kind of the thing that I was mentioning at the beginning. So there were some research that has been done quite recently. There is another paper that was just published last year with similar stuff, claiming that if they use, if they kind of quantify the bed load by the dimensionless bed load, and they compare that with the dimensionless best shear stress, which is basically just taking the best shear stress and divided by this factor, then you won't get a good collapse when you predict the bed load. Like typically, if the best shear stress was explained in the bed load, all these data points that you see here should collapse along this line. So it's quite interesting because this paper was released after my model of best shear stress in emergent canopy, and basically what they were showing was that it's like we tested the new model for predicting best shear stress, and we still are not getting good collapse with the data. But if we take, for example, the Mayer-Peter-Mueller formula, which is in terms of the best shear stress, and we recast that formula now using the TKE, and this is the funny part, they use the way that they recast TKE is by this expression, and this expression is an empirical relation that just is valid in very bad cases, but they still use it for vegetation. And basically they can recast, as I was saying, the bed load transport formula for Mayer-Peter-Mueller into a formula that now will have a turbulent kinetic energy, which is also dimensionless, and a critical turbulent kinetic energy. So when they did that, this is what they found. They say, okay, this is why they were saying turbulent kinetic energy is dictating the bed load transport. Look how the results are with the best shear stress, even the ones that Conde et al. Are proposing. Look at how the best shear stress measurement looks when you use the recasted Mayer-Peter formula. So this is something that for us was very challenging to think about it, because we were confident about the best shear stress model. So we had to look into what they were doing when they were applying this Mayer-Peter-Mueller formula, right? So we were saying, okay, so we know that they are actually using our model, and what they are finding is that if you extrapolate the bed load transport all the way, or try to get like a sense of all the bed load transport all the way to zero transport, which is going to be a very small value of transport that's kind of like just a curve here, what you will see is that actually the critical value for incipient motion when you have vegetation is actually lower than the one that is predicted by the chills. These two curves here are the ones that are predicted. It's like the critical value predicted by chills. So we say, okay, so if you combine the best shear stress formula with a reduced critical chills parameter, you should be able to get a better prediction of the bed load transport. And the reason behind that, or the physics behind that, is that when you have vegetation, you will have an extra turbulence that is affecting the velocity field near the sediment grains. And this velocity field will actually change the pressure field that is felt by the grains, which in general, if you go to the most fundamental part of the shield parameter, or the critical shield value, is just a ratio between the lift force that you get and the apparent weight of the sediment at the end of the day. So it's physics of two components, of two forces that are getting there. And the hypothesis that we were saying is, okay, in vegetated flow, the lift force is actually higher than what you get in a bare bed scenario. So therefore, the chills curve to predict the critical value is not the appropriate one. So locally for us, there was some research of grouping Professor Rafael Tinoco from Illinois, that they did some measurement of they did some estimation of the critical value of the chill parameter for emergent canopy flow, and they found a relationship. There was a parametric relationship at that time that actually was saying that the critical value depends on the canopy density, and it basically decreases. So what we decide to do is say, okay, as we know that the threshold for incipient motion is actually lower than the one that is typically predicted by the chill score, we're gonna incorporate that into our model and test the predicted bed load transport against the measured bed load transport. And when we compare our result with the turbulent kinetic energy, we again recover a good collapse. So basically what we were saying is we are not assessing which model is better. We were just trying to find the missing link, because the TK seems to work, but the Bezier stress wasn't working. The reason is, first, they weren't measuring Bezier stress in the region where you need to measure if you want to properly get that value. And the second is, when they were testing the models for bed load transport, they were using a wrong critical shear stress value, because they were using the chills diagram to predict that. And when you are in vegetated flow, this doesn't work anymore. So if you consider these both things, basically your prediction of bed load transport, which is again this line, this thick line here, against goal as expected, and kind of like the physics meaning of all the process of stress and being driver of sediment, work. However, then it comes the question, which is what's the final part of the PhD. So the question is, okay, is the TKE or is the shear stress? So because at the end what you are telling me is that now if you do a proper estimation of Bezier stress and a proper estimation of the critical chill value, you can get a good estimation of bed load. And if you use the TKE, then you're also gonna have a good estimation of bed load. So there should be something that links both of those ones. And this is actually what is one of the main results of the first paper. If you notice, I never defined how did I estimate the bottom boundary layer thickness. I just say that it has an inverse correlation with the density, like as you get denser, the thickness of the bottom boundary layer decreases. But actually what we found is that you can actually explain the bottom boundary layer thickness in terms of the turbulent kinetic energy at the top of the bottom boundary layer, or at the top of that layer. So what it means is that if you have high turbulent kinetic energy, you're gonna have a very thin bottom boundary layer thickness. And if you recall our model of Bezier stress, if you have a thin bottom boundary layer thickness, you will have an enhanced Bezier stress. So basically what is happening is that the turbulence is actually making a very thin bottom boundary layer thickness, which in turn is creating a higher Bezier stress. So we say, okay, but this is from average quantity. So it cannot be, this is just a correlation, it's not a causal relationship that you can say that high turbulent kinetic energy will actually leave you with a thinner bottom boundary layer thickness. So what you can see here is kind of a density map of bottom boundary layer thickness, but now it's not spatially average. So you will have here three types of canopy density. And what we're saying is, if I take individual velocity profiles and I just calculate the bottom boundary layer thickness and also measure the local turbulent energy there, I can see the same correlation that I found in the spatially average value. And what I found is that where you get most of the points or the velocity points there, you will have that they follow the same trend that you get in when you have the spatially average value, which means that it's not a property that happens just when you average, it's a property that happens locally. So if I just go to any point in the canopy, measure the bottom boundary layer thickness of this profile of this velocity point, what you're gonna get is a high you're gonna get if the turbulent kinetic energy there is high, you're gonna get a thinner area. If you move to another location and then again do the same, it will be the same inverse relationship that happened with different canopy density. So this was kind of like the end of the result of what we found of the PhDs, that at the end of the day, it's not that the TKE or the vector stress is a better or a bad predictor of the bed load. It's actually that in vegetated flow, they are related. High TKE actually is making, as I just said, a smaller bottom boundary layer thickness, which actually enhances the vector stress. So this was kind of like, if you scan, this will send you through this paper, so you can actually go through all the details, because there is a lot of formulations of how we can define that turbulent kinetic energy at the top of the layer, or get a proxy of that turbulent kinetic energy at that location, so you can actually have a look there, or we can discuss further in the question. So the other thing that I wanted to show is something that in the story that I was telling you, I wasn't mentioning, was the impact of that Kelvin-Helmholtz instability in the flow within the canopy. So as you were saying, I was taking a spatial average of the velocity field. However, the way that we did is that we basically get the energy of we get the non-dimensional spectral energy of the velocity fluctuation within the canopy. So we have three types of density. We have dense canopy, transitional canopy, and a sparse canopy. And we calculate this parameter that we kind of like measure the energy of different frequency within the canopy. And I just normalize it just to compare which frequency were within the canopy. So you see the dashed line, this is the canopy top. And then basically this frequency that you were getting are frequency that we might know. So for example, we know that if we have a Kelvin-Helmholtz instability, we can kind of predict the frequency that we expect depending on the average flow velocity and this is what they call the boundary layer thickness, but this is not the bottom boundary layer, this is the layer of the mixing layer that you get at the top of the canopy. And if you calculate that, it's going to be this thick line. So what you see is that you are getting, for dense cases, high energy at the Kelvin-Helmholtz instability just at the top of the canopy, and little of that energy actually penetrates inside the canopy. And this is similar to what I said. You have vortices that form at the top of the canopy, but if the canopy is dense, it will confine those vortices or the turbulent fluctuation around the top of the canopy. As you start decreasing the density, then you see that that energy can actually penetrate more within the canopy. And then, of course, if you have a sparse canopy, then you will see that frequency all the way there. The other two frequencies that you can actually see is the vortex shedding frequency, which is the frequency that you will get from the wakes of the cylinders. So you can see in the dense canopy, which is this dashed line that you get there in the transitional here. And in the sparse, it's just here. And the reason is just because, remember that this comes from a velocity field that you get from the PAV. So the sparser the canopy, the farther will be the canopy elements. So basically you won't see the wake of the next element here, so you won't see that one. And this one is just for purpose of showing the image, is just around here. But as you get denser, then you will see the vortex shedding actually showing here. But then what we found quite interesting is that there was another frequency that actually was in all cases that was happening regardless the density of the canopy. And this is what has been reported. Professor Mandel reported in the surface, when they were capturing the perturbation in the surface by submerged canopy, they were capturing a second harmonic or something that has double the frequency of the Kelvin-Helmholtz instability. And those frequencies, what was surprising for us, is that even for dense cases, you could actually see them all the way through the canopy. So imagine that you have a canopy that is not filtering out those vortices, even though it's dense. That was the traditional, what we expected. Well, this density might probably altering, and might not, it will be altering the near bed flow hydrodynamic, because as I'm plotting here, this black thin line is actually the thickness of the bottom boundary layer that I was mentioning before. So if you see that you have frequency that actually are penetrating up to the, or inside that region. So what we did at the end of the day was to try to get instantaneous stress events, and we found that this instantaneous stress event was actually important based on this frequency. So there is a clear impact of that frequency in the structure of the near bed, and also more importantly is the second time that we report the frequency now in the other part of the water column, because it was reported at the top, but now I'm saying, or we are showing that it's actually also happening at the bottom, and it needs to get further investigation. So at the end of the day, this is just the animation of this, how this instability will, you can observe then in the flow. Basically here you have the string-wise perturbations U prime, W prime, and then you will have ejection events and sweep events that actually are altering the near bed flow hydrodynamics. And if you see, you can actually see correlation between, this is probe 1, which is this plot here, and this is what you get within the bottom boundary layer, which is probe 2, and this again from PIV measurement. So you see that sometimes you will have very high sweeps and ejection event that you can record it at the bottom, but there are events that you have sweeps events and ejection event that you won't record at the bottom. So sometimes we believe that it could be related to the second harmonic that we are saying. Like if you have a Kelvin-Helfman instability that is the normal frequency, you will be filtered out by the canopy, but if the one that it turns to be is the second harmonic, is probably not being able to filter out and will alter the near bed hydrodynamics. So in conclusion, basically we have 4 main take-home messages that we can say. First one is that the bottom boundary layer thickness is primarily controlled by the turbulence generated by the vegetation. This was the last plot that I told you, that I showed you if it was visual stress or TKE. We also were able to kind of claim that if you have accurate estimation of visual stress and the critical threshold reduction, then you can get a good prediction of bed load transport in vegetated flow. So basically you need both, not just a good model of visual stress, but also this reduction in the critical threshold for incipient motion. And then if you want to talk about the structure of the stresses, the vertical structure of the stresses, then we know with confidence that the sparse submerged vegetation resemble more to the very bed scenario in terms of stresses, and the dense vegetation resemble more to emergent case. And the last one, that was the last that I showed you, is that this Kelvin-Helfman instability alters instantaneous values of shear stresses in the near bed region, especially if some of them, what you got is these second harmonics that are not being able to filter by the canopy. So that was pretty much all that I have for you to show you. Thank you so much. I think that it took 50, so hopefully there is time for questions.
We have time for a couple of questions.
Yep.
Actually, yeah, go ahead.
So in the beginning you were talking about how it was difficult to measure the velocity near the bed.
Yep.
How were you able to do that?
Yeah, so basically that's a really good question. So as I was saying, we were using PIV, so particle image velocimetry. So the idea is that you seed the flow with some particles that are neutrally buoyant, so they will follow the flow. And then what you do is that you use a laser sheet to illuminate those particles, and then with the camera you take picture of them. So this is the field that you were getting, and basically what you do is that you try to track the motion of those particles by correlating them a small sub-region of the field of view that you have, and then you can get the velocity. The thing is that when you get closer to the bed, the number of particles that you get are less. So it's hard for you to keep track of the particles. So people have developed different techniques like particle tracking velocimetry, which will say, as I have few particles, then I will probably be able to track individual particles. But that technique, instead of time, is more time consuming and actually a little bit more difficult than PIV. So we ended up kind of using something that is called ensemble PIV. So this is something that is being used for micro PIV, where they have the same issue, like they have a little bit of particles and they need to improve the correlation between the particles. So what it does is that you take picture at very high frame rate. So in my case was from 125 hertz or frames per second up to 500 frames per second. So it's like a super fast camera. And then what we were doing is that we were taking subsample of these 500 images and taking the average, let's say, of 10 images. So if you average this thing, the correlation of these 10 images, you actually increase the signal to noise ratio, and you get better correlation that will actually get you a more accurate field velocity that then you can use to study turbulence, because the issue with the average part is that if you average too much, then you get rid of the turbulence. But still, as I have 500 frames per second, and I was averaging just 10 images, I still have an effective frame rate of 50 hertz, which is more than enough to capture turbulence properties. So that was the way that I could do, or that I could find to get this bottom boundary layer thickness measurement, actually. And velocity field inside that.
What was that animation from 2 slides ago?
This one?
Yeah, was that from
Yeah, this is measurements.
okay.
Yeah, this is from the BAB.
About numerical experiments, you
Yeah, so basically with the numerical modeling, what we were doing is that we were combining both of them. And the reason was that, if you see in all our results that I was presenting, the two colors is that one is numerical and the other one is experimental. So the experimental one was the one that we have different Reynolds number, and the numerical we just have one. So we were just combining the open form measurements and putting together to kind of like increase the data set and the universe of measurements. But I didn't show it here because it was not part of the story, but we also used the numerical modeling to inform which were the best location to actually capture the spatial variability of the variable that we wanted to measure. Because the main limitation of the PAB is that we have limited location, so we couldn't measure all the places that we wanted to get a fully average, spatial average. So we used that numerical modeling result. I have the capability of result 3D, the flow in 3 dimensions. We could actually get the full spatial variability in the numerical modeling. So we were combining both, but also using that to inform where were the best location to actually do measurements with the PAB.
Your numerical experiments, one of your early slides, you showed a figure of your numerical domain. It looked like it was 2D in the horizontal. Did you actually?
Yeah, that was just a top view. I can show you. Let me just.
So you did do 3D models?
Yeah, it's a 3D. It was a 3D. Yeah, it was a 3D.
Great.
It's just the top view of how we did the element array. So basically, we just have this staggered array. We're just saying that we did 6 cyclic boundary condition because we also need to guarantee that the flow is fully developed, canopy flow developed. So we just basically running the model in this small domain because open form modeling takes a lot of time. So we were just running as a cyclic boundary condition, 15 flow through to guarantee this fully developed condition. And then we were taking average after 45 flow through to kind of like get good statistics for the time average, basically.
I see.
And this is just a top view. I should have put the top view. So it's a 3D model actually. It's not 2D.
No fluid structure interaction, I suppose. Just keep those pieces of grass totally rigid.
Yeah. So they were truly. We just impose a non-slip boundary condition as well, just to develop. So basically, if you see the rod around, you can get like a bottom boundary layer if you measure it, because as they were rigid and fixed, you were just imposing that you can actually develop their bottom boundary around the element. I was trying to show a picture, but I didn't put many animation of the numerical modeling in this one too. I just integrate the whole data in one plot.
I think we're a little over. I think if it's like a quick question, I think we can do it. Or everyone Tracy, so welcome to
Professor Mandel's got lots of questions.
I guess one of my questions is do you have opinions on if we want to move the community towards using veg shear stress model, how do we better measure it in the lab and in the field?
Yeah, so I think that the next step is to properly define what we call the critical incipient value of the Shields parameter, which means we are quite confident of the veg shear stress model that we develop, at least in terms of, I mean, keeping in mind that there are limitations of the model. Like you can apply to field condition as, I mean, with a lot of like restriction in terms of like if you are thinking about seagrasses, then there is flexibility that is going to be impacting the flow. But in ecosystem like the mangrove, where they are stiff and emergent, you will get probably a better performance of the model. But still, if you don't know what is going to be the critical value for that, any of the formulas will work at the end of the day. So I did another test. I didn't present it because I knew that project could have taken longer, which is testing all the available formula for bed load transport using the new bed stressors model and the modified critical value. And most of them actually perform quite well once you define both. So at the end of the day, now the bottleneck is to define that critical. So I picture like experiments of trying to reproduce a chill core, but with different canopy densities at different sediment sizes. So in order to kind of like properly estimate that. Otherwise, I have to be honest, I always say, you can still use TKE because TKE is a way to use it. It's just that I was telling you, it's just two approaches. Like the one is from the energy approach, and the reason why you have a critical energy that kind of like a settle when the sediment will move, it doesn't depend of if there is vegetation or not, because it's a critical energy. Whereas if you have a critical stress that you need, this comes from a force balance that you need to accurate kind of like specify. But again, there is a lot of physics that have been developed in terms of stress that is probably worth it to have these critical values solved, and then you can use the physics that we know from the beginning for those predictions.
Well, thank you.
Some more